This is the Physics 2211 Lab 4, Oscillations. The purpose of this lab is to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. Then we will attempt to construct a model which replicates the motion and plots the kinetic, spring potential, gravitational potential, and total energy. We will do this by using Tracker, VPython, and VIDLE, as well as our knowledge of Newton's second law, Hooke's law, and the energy principle. Then we will address what if and what does it mean questions, discuss sources of error, and come to a conclusion. And the conclusion was that the model can correctly predict the motion of the spring mass system as well as the energies and total energy, which remained the same, although there was change in kinetic and potential energies. So here are the equations used: Newton's second law at the top, then Hooke's law, then the energy principle, kinetic energy, spring potential energy, and gravitational potential energy. Here were the initial conditions. The object mass had 0.402 kilograms. The spring constant was 6.83 newtons per meter. The x-axis period of oscillation was 1.65. The y-axis period of oscillation was 1.50. The L0 of the spring was 0.123 meters, and the stretch length was 0.7 meters. Here are the tracker results. So to the right is a screenshot of the tracker program with the points signifying the center of mass for that object at that time. Additionally, there are two graphs showing the x and y plot versus time of the weight on the spring. It is clear that there is uniform oscillation on both axes, despite the complex-looking appearance in person. The data was found and exported to an Excel file and converted to a CSV file for use in the model later. So here are the model results. This is what we see when we run the model. The spring is represented by light blue helix, and the mass is represented by the blue ball. The blue arrow is the spring force. It is always pointing towards the attachment point, and it varies in length, representing the magnitude. The black arrow is the force of gravity. It always points down and remains the same length. It is a constant force. The red ball is representative of the tracker motion. This is where the mass would be if the two motions were overlaid. Finally, the blue line draws out the path in which the mass takes when oscillating. So here we see the model result of the program when the two motion data from tracker and the model are overlapped, and here we'll zoom in a little bit so we can see it better. Obviously there's very little discrepancy between the two, with the tracker motion just being slightly offset. So what does it mean? Is the energy principle satisfied? So yes, we can see to the right is a plot of our model, and we will zoom in a little bit. And here it is a little better. So the energy principle states that if the system is closed, then the total energy of the system will be equal to 0. So there's the equation for the energy again. And as we can see to the right, the kinetic energy, which is represented by the blue line, the gravitational potential energy, which is green, and the spring potential energy, which is red, all add up to equal 0. Where the total energy is the yellow line, and the yellow line stays at 0. So for the what if question, we were supposed to compare the period of oscillation for the x position data in second and the y position data in seconds, and compare the two. So for the x, I got 1.652 seconds, and for the y, I got 1.508 seconds. And I believe this is because the reason the y is smaller is because the y has more forces, more components of the force acting on it through the spring force and the gravitational force, and therefore the time it takes for it to oscillate is smaller. So for sources of error when using the tracker to plot the mass, it is often hard to get the points in the direct center of motion. Also, the difference between the real-world model and the computer model include the fact that the real-world model has a little bit of drag, which the computer doesn't. And another is slight syntax errors in the code could lead to major changes in the model. So by using the initial conditions set by Tracker, I was able to almost replicate the motion of a spring mass system with multiple directions of motion by using a VPython and VIDLE model. The modified energy principle outputted the results with the kinetic, gravitational potential, spring potential, and total energy of the system all appearing very similarly to what we would expect to see.